This conference will now be recorded.
All right, Math 211, this is section 2.9. I wanted to do examples 3 and 4. That way that when we come back to class next week, we will just do 5 and 6 and then move on to the next section. So the example 3 is not one we would ask you on a test, but it's a good visual of what we're really doing in these linear approximation sections and kind of how we talked about how it's really only good within a margin of error around a certain value. So we're going to show you on Desmos that we will determine the values of x that this estimation would actually be good for around a equals 0. And so we want to be accurate within 0.1. So depending on what your accuracy rating is, this will look slightly different in the neighborhood. So this is the approximation, and you can prove that by taking the derivative. So I'll go ahead and just do a proof real quick of how this happens. If you plug in just 0 into the function, you'd have 1 over 1 plus 2 times 0 to the 4th, because this is the function we're basing this off of. And that would just be 1. Now, if you find the derivative, remember we would want to rewrite that f of x as 1 times 1 plus 2x to the negative 4. So f prime of x would be negative 4, 1 plus 2x to the negative 5 times the chain inside, which is 2, which makes it negative 8 over 1 plus 2x to the 5th. And if you plug in 0 here, because remember that is our a, you get that that's negative 8 over 1, which is negative 8. So notice that's where they got this from. This is the formula, remember, f of a minus f prime of a, or excuse me, plus, because it's a minus because of the sign, plus f prime of a times x minus a, where a is 0. So this is where they got this from. So we know that that's actually the linearization or the linear approximation for this at the neighborhood that we're going to determine around 0. So I'm going to take you to Desmos, and we're going to actually show you how I could have graphed this and found that intervals. Because like I said, you can't really do this without a calculator or a graphing utility. So here's kind of what we're doing. Since our accuracy is supposed to be 0.1, we would say let's take our function and subtract 0.1 from it. And then let's put that linearization in the middle. And then we're going to take our function and we're going to add it. So in other words, we're going to take our graph, and all we're going to do is we're going to pretty much add and subtract that error value from it. So I've already set this up. If you want to see, let me click on the link. Actually, it won't let me go there directly without turning off the ink for a second. We'll save our changes. Actually, it doesn't matter so much if we save the changes. Let's just click out of that. So, because we don't really need anything else here except being able to click on the link. And for some reason that did not work. So let me try it again. If it doesn't work this time, we'll just retype it in. There we go. So I've already preset up kind of the situation here. So notice that I'm going to zoom in at 0 because that's where we're focusing on. If you want to see what this function looks like, we could zoom out. This is 1 over 1 plus 2x to the 4th. Notice it's going to, at negative 1/2, it's kind of going to positive infinity on both sides because of that asymptote there. So let me zoom all the way in at 0, because at 0, the function's value we know is 1. Now, you can't really see very good how it almost looks like a straight line. So you can't really see very good the red line anymore, which we don't really need. Because what I did was I came up with what would happen if we shifted the function down 0.1 and if we shifted the function up 0.1. So if you zoom out here again, you can kind of see this is just the function shifted up and down that error, margin of error 0.1. And if you find the black line, it will cross these dashed lines in 2 places. So let's see if we can find that first point. There it is. So it crosses this purple line. It actually never crosses the green line in this neighborhood, but it crosses the purple line first at negative 0.0454. The other place it crosses a little further down here on the other side of 0. So notice that's 0.0554. So around this neighborhood of 0.0554 all the way up to, we said negative something. Let's write these down. So it's negative, I'm going to type them right here, negative 0.0554. 454. And the other one was, so this is just so we can remember them, 0.0554. So what we're saying is that if we want to keep our tangent line approximation within 0.1 of the curve, because even though this looks like a big gap, we are zoomed in extremely. This is about a 0.1 difference where we had that right here. So it's exactly about a 0.1 difference between them. So we're saying that this tangent line approximates that curve within a 0.1 error in these regions of x values from negative 0.0454 to 0.0554. So notice it's not a huge region at all, but at least we now know that that's when the approximation is a pretty decent approximation. So you could set up different margins of error if you wanted to. You could have a margin of error of 0.5 or 0.05. The tighter the margin of error is, the smaller the interval is going to be, because you're going to be dealing with less, flexibility in it deviating from the curve. All right, so that's just so you can visually see that and kind of understand that that's what we're doing. So example 4 is we're going to be finding dy, the differential. So we have to remember what that means. So let's write down what that definition was. It always jumps down when I do that. So we're back into ink mode. So remember we learned in the definitions from the class session we had that dy over dx equals f prime of x, which means dy can be rewritten as an dependent variable on f prime of x times dx. So if we're wanting to evaluate the differential dy, we have to first of all find these f prime and put this together in our equation, and then we can evaluate it for given specific values. So let's take the derivative of this, because this is like our f of x here. So if we take the derivative of that, that would be negative sine pi x. And because of the pi inside there, we have a chain rule of pi. So that means that dy can be rewritten as negative pi sine pi x dx. Okay, so there's dy. That's the first portion of this problem. The next thing is we want to plug in a 1/3 for x, and we want to have a change in x of negative 0.2. So if we plug in those pieces of information, that makes that pi over 3, and this becomes negative 0.2. We know that pi over 3 is square root of 3 over 2. So I have negative pi times the square root of 3 over 2 times negative 0.2. That's negative times negative, so that actually makes it positive 0.2 square root of 3 over 2 pi, which I would probably work out. You could rewrite it as 0.1 square root of 3 pi if you want to reduce the decimal and the number at the bottom, but it's approximately 0.054. So that is the dy evaluated at those two specific values. And then the other one I wanted to do real quick is just, let's do one that is a quotient rule. So that this is our f of x, then we need to find our first derivative to be able to write the dy, the differential dy. So this would be bottom times derivative of the top, which top is just going to have a derivative of 1, minus the top times the derivative of the bottom, which also has just a derivative of 1, all over the bottom squared. So f prime of x is going to be x minus 1 minus x minus 1 over x minus 1 squared, or f prime of x is the x's on top cancel, so it's negative 2 over x minus 1 squared. So that means my differential dy is negative 2 over x minus 1 squared dx. And when we plug in the x is 2, so I'm going to go ahead and circle that. That gives me negative 2 over 2 minus 1 squared, and then my dx is change in x is 0.05. So this ends up being, that's going to just be negative 2 times 0.05. So I get negative 0.10 for dy. So these aren't too hard. It's just you have to know what the definition of what is the differential dy. And remember, we just found that by taking dy dx, which is derivative of y with respect to x, equal to f prime of x, and we solve for dy. So that's where that comes from. And that is it for this video. Like I said, we'll do example 5 with the delta y and dy at the same time, and we'll do example 6 together on our next class session.